So let's discuss about capillary electrophoresis, right? So I'm sharing my screen here, the PPT, right? Now, when it comes to capillary electrophoresis, as the name suggests, you are using capillaries. Electrophoresis, when we say, what comes to your mind is the electrophoretic unit, either horizontal or vertical unit. But as in the first lecture we had discussed, the electrophoresis system with reference to support matrix and without support matrix, that is liquid electrophoresis and electrophoresis with support matrices. In support matrices you have cellulose acetate, you have paper, you have polyacrylamide gel, you have agarose, so on and so forth. Right now, these materials and matrices, they are going to do a function that it is going to have a sieving effect, and so mobility of the molecule will be based on not only the charge, the direction of the mobility is based on charge, and the speed of the mobility is going to be governed by the molecular size as well. But when it comes to capillary electrophoresis, it is another technique which is still under process. That is what people are saying. Of course, every technique keeps on emerging and evolving and comes up with a better performance, right? We know that. So in this case, in capillary electrophoresis is carried out in small capillaries, right? So when we say capillary, the inner diameter is going to be very small. So as indicated here, it is 20 to 100 micrometers inner diameter is there. The capillary provides a high surface to volume ratio, right, and allows very efficient dissipation of heat generated from applied electric field. We know in electrophoresis the buffers are going to be important because they are going to help in conductivity, at the same time they are helping in heat dissipation. All right. So here also heat dissipation is a major issue whenever we are applying current. So the system will get heat up and that will denature the molecules. So dissipation of it is very important, and capillary electrophoresis system is said to be good in terms of heat dissipation. The third point about capillary electrophoresis against that of standard gel electrophoresis, here we are applying very high electric field which is going to overheat the gels or in the capillary. So you have to have a efficient system that would dissipate the heat. So in a capillary electrophoresis, electric field up to 800 volts per centimeter is applied. So applied voltage up to 30,000 volts could be there. But of course, if heat generation is allowed, then separation is going to be a challenge. Diffusion will be more, and denaturation of the molecules will be more. But capillary electrophoresis is the one which is having this benefit, that is dissipation is good. Also, the capillary gel electrophoresis is combined with laser-induced fluorescent detection methods, or fluorescently labeled DNA can be added into that, and then detection system. Because anyhow, when we run any electrophoretic system, the gels are to be documented. You have to analyze the bands form and correlate with the properties and study the molecule. In short, may it be molecular mass, may it be the conformation, whatever may be, maybe hybridization pattern, whatsoever it may be, right? So here also for detection, you can connect the system with the detection systems like laser induced fluorescent detection, one of the examples. All right. Now this was an overview. Now let's go into the details along with the structure of the design. Of course, when I say capillary electrophoresis, it's a family of techniques. It is not single. So you have capillary zone electrophoresis, you have capillary isoelectrophoresis, focusing. Isoelectric focusing as a separate topic we have learned already for two lectures. So you know what isoelectric focusing is, but it is conducted in capillaries. Similarly, capillary gel electrophoresis, then capillary isotachophoresis, micellar electrokinetic capillary chromatography, capillary electroosmotic chromatography. So this is how you have the variants of basic capillary electrophoresis system. Fine. Now, as far as your syllabus is concerned, as the one of the advancement in the electrophoresis, we are talking about capillary electrosystem. So as you are seeing, here are the two reservoirs, right? And this is the capillary which is dipped in both of them, one end in one beaker reservoir, and another end in the another reservoir. And here is shown the migration of the or mobility of some analytes. They are shown in colors so that they are I mean, just to make it visible. So the diagram should be just to give an idea about how the things work. So they are shown in colors zones, right? Here is another design where you are going to have these two reservoirs. All in the reservoirs are dipped the electrodes. These reservoirs contain electrolyte solutions, naturally like buffers that you have in electrophoresis. And this is the capillary tube. Now it is like an arc it is shown, and this is the current source. So DC supply is there, about 50 kilovolt DC is applied. And if you see the capillary, the inner diameter of the capillary, as I said earlier, is in the range of 10 to 250 micrometers. And these are few silica capillaries. And here the current is applied, and it is going to carry out electrophoresis process and separation of analytes. So this has been referred to as high performance system or a high throughput system. Uh, Now, as the name suggests, capillary electrophoresis, as you can see in the diagram also, you are going to use very narrow bore tubes, right? As I said, the inner diameter is around 50 to 250 microns. So advantage of using capillary is that they reduce problems resulting from heating effect that we have talked earlier, right? Small diameter of the tube there is large surface to volume ratio, and that is going to give a good or enhanced heat dissipation. Now, because heat dissipation is there, it is going to help eliminate two things, that is zone broadening and convection currents. Again, convection currents are going to lead to zone broadening. So separation is not going to be really good if there is convection current working or the diffusion is facilitated. So these two problems are taken care of when we talk about capillary electrophoresis. Right. So because of heat, diffusion is going to get facilitated, and that is going to cause broadening of the zones. So both these things are taken care of when we are using capillary electrophoresis. Now let's look into the basic important equations which are related to capillary electrophoresis. Now here I am showing first equation, that is T equal to L square upon mu upon V. I'm sorry, here it is mu is small and V capital, right? Yeah, this is the equation. So T is the time for migration, L is the tube length, V is the voltage applied, and mu is the electrophoretic mobility of the analyte. How to calculate mu? We have learned it earlier also. Now, this is one equation, and second equation which talks about efficiency of the process, how good separation is going to be achieved, is very much like that in chromatography we had talked, right? Theoretical plates concept, that is the total length of the chromatographic column, or in this case that of the capillary tube, and the separation of the analyte between the zones, that is mobile zone and stationary zone. Even in electrophoresis you have both mobile zone and stationary zone. The gel matrix is the stationary zone and buffer is the mobile zone. Similarly here, this distribution, when we talk about the analyte between the two zones, mobile phase and stationary phase, then it going to reach to equilibrium. So the equilibrium between the mobile and stationary phase distribution of the column, of the analyte in the column, is described in terms of theoretical plates. So this is referred to as a theoretical. The word itself tells you it is theoretical, that is the distance or the zone that is required uh, to have equilibration between the two phases. So equilibration is not going to be attained once and the story ends. As we have learnt in calculations related to theoretical plate in chromatography, you must be remembering that this is going to be a continuous process throughout the length of the column or throughout the length of the capillary. So length of the capillary, number of such zones, height of each zone, all these things are very important. So that is going to decide the efficiency. So n is a theoretical plate, that is the distance that analyte will migrate, and while migrating it will get distributed between the two phases, that is mobile phase and a stationary phase. So degree of distribution will depend upon the nature and the interaction with the two phases. If it is stronger, it with the solid phase, it will be retained. If it is more with the mobile phase, it will be moving fast. That we know with respect to chromatography we have learnt. Similarly here, N is the concept, that is theoretical plate. Again here, U is the electrophoretic mobility, so it is small mu, and V is the voltage applied. So the second equation is N equal to mu V upon 2D. What is that? N is theoretical plates, right? Theoretical plates, theoretical plates, and D is the diffusion coefficient. Now diffusion coefficient is going to be entirely the property of the analyte under study, its size, its net charge, or and density of the mobile phase. All these things are going to govern the diffusion, right? So diffusion of the analyte is going to be uh, its own property, so it is denoted as a constant and denoted by symbol D. So diffusion coefficient uh, and voltage applied and electrophoretic mobility are the components in this equation. Now from these two equations, what do we understand? We understand that the length of the electrophoretic column, capillary, है, plays no role in separation efficiency. कितना छोटा है कितना बड़ा है is not going to play any role. But it is important that how it influences on migration, how it influences on migration time, analysis time, that is important. And when I say how it influences migration, it means how it influences or decides or facilitates good separation. That means high separation efficiency that is to be achieved. So use of high voltage is going to be important, that is going to decide the mobility mu, and also it is going to control the diffusion. So diffusion constant D also, which is dictated by solute, which cannot be much manipulated, but yes, under applied electric current, it is going to be moving, and diffusion again is going to be controlled only by one factor, that is the high voltage that you are applying, right? So when we talk about these two equation, it appears that ideal situation where you are applying a very high voltage as much as possible. Why you want to apply high voltage? So that the electrophoresis time is reduced. So a short capillary electrophoresis time is there, and you can use a short capillary also. So this is one thing that is clear from these two equations, right? Now, are there any limitations? Yes, practical limitations are there to this approach, because if you increase the capillary length or if you reduce the capillary length, what kind of problem are they going to create? So, if the capillary length is reduced, the amount of heat that must be dissipated increases. How will it will increase? Because it will increase due to decreasing electrical resistance of the capillary. At the same time, the surface area which is there for heat dissipation, it is reduced. So thermal effect will occur, and then a very short tube, if you have, it will get heated up very fast. So reduce the capillary electrophoresis timings. If you decide to increase the voltage and reduce the capillary size, you cannot get good separation or good efficient process, right? So there are limits how short a tube can be used, right? That is first point. To understand that, these two equations are been. Secondly, we say कि very high voltage is applied. So greater the current, faster is the mobility, but at the same time, more is the heat generated. So in practical terms also, you have to work within certain limits. So voltage about say 10 to 50 kilovolts for capillaries up to 100 centimeters are commonly used. So this is the basic apparatus that we have seen in the previous slide, right? So a small plug of sample solution is introduced into the anode end of the fused silica capillary tube. So I just go back to the diagram again. So here you have two reservoirs, right? Two electrodes, and this is one end of the capillary tube, and this is another end of the capillary tube. So you have to use the plug. What do you mean by plug? That is, say, for example, agar block. If I take, it can be called as plug. But here you are going to use say uh, uh, the small plug of sample solution, and it is introduced into the anode end. You are not going to take agar, but it is going to be uh, some small material that is going to carry your sample, right? So a small plug of sample solution, of course they are available. You have to inject your sample into that. They are readily available along with the kit or the instrument itself, right? So you have to inject the sample solution, and the volume of the sample solution that is required also is very less. In few microliters of sample is required, right? You are going to introduce it into the anode end of the capillary. One side is anode and another side is cathode. So in the anode end, you have to insert that plug in which you have loaded the sample, and uh, you have to start the process. But loading the sample also can be done in two ways. One is high voltage injection, and another is pressure injection. When I'm talking about high voltage injection, with the high voltage switch off, the buffer reservoir at positive electrode is replaced by a reservoir containing the sample, and a plug of sample that is you have prepared is introduced into the capillary. So what does it mean? You are going to apply very high voltage for a part of time, and at that time you are going to insert your sample plug. The sample reservoir is then removed and buffer reservoir is placed. That means you are applying a current, and here in place of buffer reservoir you have kept sample reservoir, and current is applied. So the migration of sample would take place in the capillary, and then you have to replace this and place back the buffer reservoir again. So sample reservoir, buffer reservoir. Initially your system is there, on both the ends you have buffer reservoirs. When you want to introduce a sample, remove the buffer reservoir, and then you are going to take the sample reservoir, keep it there at the side of anode, apply the current so that sample will move, migrate into the capillary. Then you are going to replace the reservoir for buffer reservoir. Again, on both sides you have reservoirs for buffer, right? So, and then again you have to apply the voltage. So separation will be continued. This is one way. Second way could be by pressure application. Suction kar lo sample ka, you can get into that. So capillary is removed from the anode buffer reservoir, and it is inserted into the sample solution, and the second tube is going to be applied, which is going to provide the pressure to the sample solution, and it will force the movement of sample into the capillary. And now again you have to replace the sample reservoir by buffer reservoir. So either with pressure or with voltage you can load your capillary with the sample, or rather I should say injected. So it is by suction or high voltage application you can allow injection of the sample into the capillary, right? And then you are going to run the system at about 50 kilovolts. So that is the voltage applied across the capillary tube, and the component molecules which are there in the injected sample, they will migrate. They will migrate at different rates along the length of the capillary. So different rates are going to be dependent on the electrophoretic mobility of each molecule. It is going, or analyte is going to be different. It is going to be its unique property. So they will migrate, and the movement of charged molecules uh, in the solution will help the movement towards oppositely charged electrode, right? So owing to the electrophoretic migration, positive and negative sample molecules will migrate at different rates. Now the analytes are separated by electrophoretic migration, but at the same time there is another factor which is going to decide the rate. What is that? It is the electroendoosmotic flow, usually which is much greater than electrophoretic velocity of the analyte. So all the ions, regardless of their sign, that means the charge, positive or negative, or the neutral species, they are carried towards the cathode. So positively charged molecules reach the cathode first, because the combination of electrophoretic migration and electroosmotic flow cause them move fastest. So Positively charged ions or analytes will move to cathode first. As separated molecules approach the cathode, they pass through through a window where they are detected by detecting systems. So as in ultracentrifuge systems, analytical ultracentrifuge, you have an analysis window or viewing window, and that is centrifuge is attached with the spectrophotometer, for example. So continuous analysis of the analytes using spectra, uh, spectra based analysis, that is refractive index and absorbance and all that is taken, and you get the continuous real time analysis and data generated will be visualized or will be displayed. Similarly here, the capillary electrophoretic system is attached to the analyzer systems. So whatever is happening at given time will be monitored through that window, and that window is just monitoring this migration of the analytes, and that analyte migration is monitored or detected with the help of UV monitors, ultraviolet monitors. So as the analytes they migrate, they will be coming in the field of ultraviolet lights, and the signals will be transmitted to the recorder. They will be integrated and computerized, and you will get the output. So generally within 10 to 30 minutes, a capillary electrophoresis run can be concluded. So this is overview for capillary electrophoresis system. Right now, next is about pulse gel electrophoresis. That is another thing that we have to talk about. Right. So what is pulse gel electrophoresis? The name itself tells you pulse field. So there are pulses, right? So fields are getting generated, and again gel and electrophoresis. These two words are there. So the agar gel method of DNA. Shall I begin with the second one? Right. I know I had to wind up the two methods today, but yes, three slides. I think I hope I have discussed and you have understood that. Is there any question? Madhura, Tanvir, Nikita?
No,
Okay.
ma'am, I'm just joined.
Yeah, I know. I saw you joining. But
Yes,
other two
ma'am.
girls here are there. But okay, now you are starting with the next technique, that is pulse field gel electrophoresis. Earlier I discussed capillary electrophoresis. All right. So when I say pulse field gel electrophoresis, we have seen in the previous lecture about agar gel method for DNA separation, fractionation. Right. So DNA of about say, 60 kilobase or less, you are analyzing with native gel electrophoresis. Now when we talk about pulse field gel electrophoresis, further development of the basic technique, you can say, you can separate the DNA of sizes say 2 into 10 raised to 3 kilobase pairs, right? So big size molecules can be easily separated. So separation of whole chromosome you can imagine by electrophoretic system when you are using PFGA, right? In one sentence to say, you can imagine separation of entire whole genome or whole chromosome by electrophoretic process. Now here, what is this method basically? It involves electrophoresis in agarose, but there are two electric fields are applied. So very first point is it involves electrophoresis in agarose. Second point is two electric fields are applied, and they are applied alternately, and they are applied alternately at different angles for defined period of times. So you have two electric fields applied at different angles for specific time slot, say 60 seconds, right? So that is why pulse it is called as. So how it works? So to say कि activation of the first electric field is there, which is going to cause the coiled DNA molecules to get straightened in the horizontal plane, and they will start to move through the gel. Now, interruption of this field and application of the second, just give me a second. Application of the second will uh, reorient the molecules, right? So they will start the second pulse in the different angle is and applied, so the molecules will move in the new direction, and alternately you are applying the first field, another field. So you are switching in the field, and their directions, their angles are different. So continuously molecules are under what you can say reorientation of molecules, and they start moving in the different direction every time. So initially there is length dependent relaxation behavior. That means your DNA was in the double stranded DNA, right? Now, give me a second. Right. So what you see in the diagram is, I'll come to the diagram little later. First, let me talk about basic points. First is it is agarose gel. Second is you are going to have pulse of electric fields. They are given at different angles and for specified time. These are the four keywords. Right. Fifth keyword is that when you have very large size DNA, maybe entire chromosome, it can be separated using pulse field electrophoresis. What is the principle of the method? The principle is separation is as per electrophoresic separation principle only, that is electrophoretic mobility of charge entity under applied electric condition, applied electric field. However, the voltage is not applied across the gel, rather it is applied towards the center and at 60-degree angle of the gel. So direction of the electric field is changed at equal time intervals. So time intervals can be, as I said, 60 seconds, but it is not that you have to stick to that. It can be as less as 0.1 second to 1000 seconds depending upon the size of the DNA molecule that is under study. So each time the direction of the electric field is changed and the DNA fragment get reoriented. So overall, the movement of the DNA molecules will result in net forward migration of the fragment. But this is going to be very important because the molecule, the size of the molecule is huge, right? So pushing that molecule through the gel with applied current, the current should be just enough not to heat up the system, not to denature the system, retaining the molecular structure of the DNA molecule or fragment under study. All these are very important factors, right? So you have to take care that uh, the heat generated should be minimum. There should be good heat dissipation. There should be good movement of the or migration of the sample DNA. All these things which are applicable to any kind of electrophoretic system are applicable here also. But the difference is, as against all other types of electrophoretic systems, here you have the very big molecules which are handled or analyzed. So that is a very big challenge, right? So when you're talking about the separation of such a big molecule, uh, then you have to give alternate fields and at a specific angle. What actually happens, why it is changed, let's talk about it. See, when you are talking about change of field at particular angle for specific time, alternately you are giving the field charge. Now point is that the entire DNA is going to migrate, that is true, but length dependent relaxation, right, is very important. So horizontal plane में जब it is going to move, and vertical plane may it is going to move alternately. So activation of the first electric field will cause the coiled molecule to be stretched. So when it is getting stretched, that means it is spreading in the horizontal plane, and when it start migrating, it is moving in the vertical plane. All right. So this is going to happen. So when you apply the field first time, uh, it is going to get relaxed, it is going to get stretched. But when you interrupt this field, the application of second field is there, the molecules will move in the new direction, as I said earlier. Now there is length dependent relaxation behavior. What is the important statement? Length dependent relaxation behavior. That means when there is a long chain molecule, it will undergo conformational change when you are applying electric field. The smaller a molecule, quicker it will regain itself. But and see, your molecule, it is in the gel. it is getting exposed to very high voltage, right? So what happens is the coiling pattern is going to get changed, the conformational change will occur, and it is just in response to the voltage applied. When voltage is applied for a fraction of second, again you are going to apply the voltage in the second field, which is alternate field, what you call it, at 60 degree you are going to apply that. Now the point is, the molecule has to regain its own conformation when the first field is interrupted. When the molecule is small size, it will attain or reverse or regain its original conformation easily in the new field and will be continue to move. So आप उसको वो थोड़ा सा झटका दे रहे हो and then allowing it to move. You are putting it under stress and then you are allowing it to move. That is how it is happening. So when that field is applied, molecule undergoes relaxation, its conformation is changed. You interrupt the field. When you interrupt and apply it at the second field, that time its mobility is promoted. So molecule is undergoing a change. There are two phases: relaxation phase and migration phase, right? So if the molecule is small, it will quickly regain itself, and regain itself when you are applying new field, and will be able to continue moving, or it will start continuously moving through the gel. But if the molecule is larger or if it is longer, it will take more time to regain, to realign. स्प्रेड हो गया है पहले झटके से, इलेक्ट्रिक फील्ड जो आपने दिया हॉरिजॉन्टल स्प्रेड हुआ है, एंड देन यू आर चेंजिंग द एंगल ऑफ इलेक्ट्रिक फील्ड so that mobility is allowed, but now it has to come back to its original shape so that it passes through the gel. पोर से उसको निकलना है. So this regain I am talking about. So it is going to take longer time if the molecule is very big, right? So mm separation time for small molecules and for big molecules will be different. Their migration, their mobility will be different. Smaller molecules will be moving faster ahead of larger molecules and will separate according to size. So for example, if you take example of say yeast chromosome, that vary in size 260 to 850 kilobases. Now all these bands have to get formed, right? Now generally what we do, we take the sample, we treat it by either enzymatic method or by shear, by shearing it so that fragments are created and then the fragments are allowed to run. Here we are not doing that. Here what we are doing, we are taking the colony directly, right? Then it is put into a small plug, agar plug, right? Sorry, agarose plug. It is inserted into that, and this agarose plug, they are exposed to uh, treatment. So you are going to denature the sorry, not denature, you are going to fragment the DNA in the plug, right? You have not extracted the DNA, you have not processed the DNA, you have taken the colony, it is put into the agar plug, and there you are uh, doing the restriction digestion, or you are exposing that agar plug to the treatment such that the DNA, the cells are lysed, the DNA is released, and then the DNA will be exposed to electrophoresis. Right? How you are going to do that? These are the small plugs in which you have your colony kept, and it is treated to release the DNA. Right? Maybe it is restriction digested. So you have fragments generated. So colony से DNA निकल के उसके टुकड़े होके they are there in these plugs now. Now these plugs will be kept on the top of the dissolving gel. So as you have stacking gel and dissolving gel,